Let's go and finish this up. So tree diagrams and conditional probabilities. Tree diagrams. I don't know if you guys ever use a tree diagram before. So let's go to page 338 on the bottom. There's a paragraph there that starts with Shannon. So it says, Shannon hits the snooze button on her alarm 60% of school days. If she hits the snooze, there's a 70% probability that she makes it to her first class on time. If she doesn't hit snooze and gets up right away, there's a 90% chance that she makes it to class on time. Suppose we select a school day at random and record whether she gets in blah, blah, blah. And so let's go ahead and show the tree diagram. Okay, so we're gonna go ahead and the alarm happens. So I hit the snooze. I hit the snooze is 60% of the time, correct? Yeah, so 60% of the time I hit the snooze, 40% of the time I do not hit the snooze. So when I hit the snooze, so here's where I hit the snooze, I'm either gonna be late or not late, right? So I'm gonna be on time and late. So on time, I am 70%, I believe. Is that correct? 70%? So the other percent of the time, only 30% of the time I'm going to be late. If I do not hit the snooze and wake right up, then I'm going to be on time 90% of the time. And then I'm going to be late 10% of the time. Okay? So what is the probability that I am on time and I hit the snooze button, right? So that would be through here and on time, right? On here and on time. So that'd be 0.6 times 0.7 would be 0.42. 0.6 times 0.3 would be 0.18 to be late. And if you look at them, you add these two together, I should get 0.6, which is this branch right here, this tree branch right here, right? Because they added together, they should be 0.6, which they are. Then our 0.4 times 0.9 to be on time without hitting it. If I multiply those together, I get this. And multiply these two together, I get 0.04. Again, if I add these two together, I get 0.40, which is 0.40, which I should get, okay? Okay, so that makes sense, right? So now the question is, if I was late, so given that I was late, what is the probability that I hit the snooze button? Okay, so if I'm late, I'm either this guy or this guy, right? And this is the one where I hit the snooze button. So it's going to be 0.18 plus 0.04. So go like that, right? You see that? Okay. So this is the given that I am late. Given that I'm late, what is the probability that I hit the snooze button? Okay. So on page 339, there is a tree diagram. There's a definition there. Go ahead and read that. Okay, should be okay with that. I'm not going to go over the example of reading ebooks or print books. Okay, let's do the mammogram one. So that's kind of interesting. Page 342, mammograms. Many women choose to have an annual mammogram to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't. It's called a false positive. Other times, the test says that a woman does not have a breast cancer when she actually does. That's a false negative. Now, okay, this is kind of interesting because with COVID and everything, now we're talking about false positives, false negatives, right? Okay, suppose that we know the following information about breast cancer and mammograms in particular. 1% of the women 40 above population have breast cancer. For women who have breast cancer, the probability of a negative is 0.03. For women who do not have breast cancer, the probability of a positive is 0.06. Okay, so let's go ahead and write this out in tree diagram. So you have 0.99, I have no cancer. 0.01, I have cancer, right? Oh, the book's got it the other way around. Cancer, no cancer, okay? So now we're gonna have we can have a false positive, a positive, or a negative, right? So this is going to be, so 0.03 at the time, I'm going to get a negative. I'm going to get a positive here. Okay, over here, I do not have it, so positive would be a bad thing, and the bad thing is what? 0.06, 0.94, so this is negative. Okay, so what is the question? Random significant population is find the probability that she actually has. So when and she's positive. So there's two ways I can get a positive, right? I can get a positive here, which is 0.01 times 0.97. I can get a positive here, which is 0.99 times 0.06. And I want to find the probability of being this guy, right? So it's going to be what? 0.01 times 0.97 plus 0.99 times 0.06 divided by 0.01 times 0.97, right? Because of the positive, of the two positive ones, I want to know this guy here, right? Okay, so that's how that works. Let's go ahead and flip the page, go to multiplication rules for independent events. Okay, so the multiplication rule, let's go and start with the general multiplication rule. General multiplication rule said what? General multiplication rule said that PAB is equal to PA times PB given A. Okay? If I'm independent, what happens here? What is this guy here? If I'm independent, if A and B are independent, this is the same as just P of B. So P of A times P of B. If they're independent, the probability that A and B, the intersection of A and B, is nothing more than A, P of A times P of B. Okay? All right. Let's see. Let's go ahead and do the O-ring one, the Challenger disaster. So in the Challenger disaster, we have what? Let's go ahead and read the problem. Eva, read the problem for us.
On January 28, 1986, the Space Shuttle Challenger exploded on takeoff. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under the cold conditions that day, experts estimated that the probability that an individual O-ring joint would function properly was 0.977, but there were 6 of these O-ring joints, and all 6 had to function properly for the shuttle to launch safely. Assuming that O-ring joints succeeded or failed independently, find the probability that the shuttle would launch safely under similar conditions.
Thank you. So you have 6 of these things, right? And all 6 of them have to work properly. In other words, if one of them fail, the whole thing fails. Okay, so This guy, the first one has to work, second one has to work, third one has to work, so on and so forth. So basically this is going to be what? 0.977 to the 6th power. Correct? Because you're multiplying it 6 times, right? Okay. So if I do that, what do I get? If I multiply that out, I get 0.87%. So even though the probability of a single one to fail is only 2.3%, when you have 6 of these things that all have to work, you're going to end up with a pretty hefty, so only 87% of the time it works. In other words, your failure rate is 13%. And as an engineer, that is way, way too big, okay? You cannot risk the entire mission on a, what is 13? 1 of 7, 1 of 8, 1 of 7, or 1 of 7.5% time. So 1 out of 7.5 times, you're gonna fail. And the failure is not just you failing to, get a popsicle. I mean, it's a catastrophic failure here, right? We're talking about the blowing up the shuttle, okay? All right, so this is not a good thing, okay? So let's flip the page and, oh, looks like we're done. We are done. Okay, so we are now done with 5.3 and we are done with chapter 5. So